All right, so we've covered the idea that we can convert an alcohol to an alkyl halide. But the question needs to be asked, well, why do we care about that conversion? Why do we need to convert an alcohol to an alkyl halide? And the matter, so why is that important? It's important because alkyl halides are versatile intermediates in organic synthesis. So they're really powerful intermediates. We can make a lot of different structures from alkyl halides. So then some of you might be thinking, well, why don't we just always start from alkyl halides? Why do we care about alcohols at all? It turns out that in the real world in nature, alcohols are kind of all over the place. So it's easy to extract alcohols from natural sources, but halogens are a little bit more rare. We don't find halogens out in nature as much. So we can't get a large quantity of a halogenated alkane to do another reaction on, but we can acquire a lot of that alcohol and then convert that to the alkyl halide. So alkyl halides are versatile intermediates. So for instance, if we wanted to synthesize something like this nitrile from this alcohol, how could we do that? If we just took the alcohol itself and treated that with a pretty strong nucleophile, the Cn-, it turns out that that's actually not going to work. That's going to give no reaction. Why is that? Well, we've already kind of covered that. Alcohols aren't good leaving groups. OH- is not very stable by itself. So what can we do instead? We know that we can convert the alcohols to the alkyl halides, so that could be our first step. So we would take this alcohol, we could treat it with HX, we could treat it with thionyl chloride, phosphoryl bromide, really any of them are going to convert that to the halogen. We'll do thionyl chloride and pyridine just because that's probably what people would do in the real world. And that would convert this to the chloride. And then at that point, we have a really good leaving group on the molecule. We could just take the Cn-, a strong nucleophile. We have a good leaving group. So this is going to be a really favorable reaction. This is going to be a really strong SN2 substrate to make that nitrile that we are potentially desiring. So again, why do we care about turning alcohols into alkyl halides? Because that makes them into good leaving groups, and we can easily acquire alcohols. They are cheap materials from nature. So once we convert those to the alkyl halides, we can make lots of other products from those, and we can do a lot of diverse types of chemistry with those alkyl halides. So that's kind of what we have here. Converting an alcohol to a halide is one option for synthesis of a leaving group. But what it says here is that more options are always better, right down here. So we're about to talk about another option that is called a tosylate, and it kind of mimics the reactivity of a halogen. So more on that in a moment. All right, so tosylate again is like I just said, it's another good leaving group. It really mimics a halogen in its reactivity, but I haven't even told you what a tosylate is yet. So that's where we're going right now. So essentially what we're going to do right now is compare these three molecules as far as how good of a leaving group is this OH versus this Cl versus this thing that we haven't really talked about yet. So as a leaving group, this OH would be OH-, this Cl would be Cl-, and this O sulfur thing, it's a sulfone. That's the name of this functional group, a sulfone. It as a leaving group would be this O-. So how does that O- compare to that O-? So how are these as far as their stability on their own? Because remember, a leaving group is better if it is more stable on its own. So first of all, let's compare what we already know about. How stable is OH- compared to Cl-? How do we compare leaving group stability? We think about the conjugate acids, because the stronger the acid, the more stable the conjugate base. Conjugate acid of OH- would be H2O. That has a pKa of 15.7. Cl minus has a conjugate acid of HCl, pKa of -7. So this is not a very strong acid, so this is a weak leaving group. Weak acids have strong conjugate bases, unstable conjugate bases. Strong acids, pKa -7, strong acids have stable conjugate bases. This is the conjugate base. It's really stable by itself. It's a weak conjugate base. So what does this compare to? And what would the conjugate acid look like? The conjugate acid would look like this, which we maybe haven't seen this exact same thing before, but what have we seen that looks really similar to this? Yeah, what do we use to eliminate alcohols? We use sulfuric acid. So this looks really similar to sulfuric acid. We've drawn out sulfuric acid's structure quite a few times at this point. Sulfuric acid has essentially the same structure as this, but this just has an R group instead of another OH. Sulfuric acid's pKa is -3, and all of these sulfur-type sulfone functional groups all have a really similar pKa to that. So that tells us that this would be a really strong acid. And again, why was it such a strong acid? It's a strong acid because its conjugate base is really stable. Why is this conjugate base really stable? Well, it's an O-, got the O- there, but what makes this one more stable? Remember, this one's more stable because the negative charge isn't just on one oxygen. It's delocalized onto that oxygen. And I'm not going to draw the third resonance structure, but we'll draw one of them at least. But if it's delocalized onto that oxygen, it would also be delocalized onto that oxygen. So essentially, why is this so stable? Because it's a very delocalized negative charge. So that's what makes this so stable, and that's what makes this such a good leaving group. And this is essentially a tosylate. I'm going to give you the full structure of a tosylate. What is the R on the next page, in the next video, but more or less, this is the tosylate structure. What this R is doesn't really matter that much, whether it's a methyl group, whether it's another big fancy thing. The thing that makes it a good leaving group is the OS with the two other O's on there that makes that conjugate base stable, makes that a good leaving group. So more on this soon.